symphony of spheres. Here we have about a 3-inch diameter sphere of water with an 1.5-inch diameter bubble inside, and we are adding more air to the bubble, and in the process of doing this it drives the bubble into some delightful oscillations. And realize this is the inverse system of what we just saw with the large sphere, where here we have a sphere of air surrounded by water. In the previous example, we saw a sphere of water surrounded by air. Now, watch at the end of this experiment. We will drive an oscillation, and after we quit putting in air, look in the center of the bubble, and what do you see? When we saw this, again, it made our jaw drop, and so we decided it was time to inject droplets directly into the bubble. So what we have here are droplets in a bubble in a sphere, which is why we call it our symphony of spheres. And we can look at these delightful interactions between these droplets bouncing around in a three-dimensional billiards game, where they interact with collisions with each other and collisions with the wall. And sometimes there is mass transfer between the droplet and the wall, or between two droplets. So why do we get the mass transfer with some collisions but not other collisions? And where does the momentum come from that propels these little drops? Watch this droplet. It will bounce 5, 6, 7 times, and then it will have a mass transfer, and it gets momentum from that mass transfer, and it gets jetted off the surface, and it bounces around inside of the bubble until eventually there will be another mass transfer, and the remaining part of the droplet gets jetted around again. Now, there was a droplet that had a mass transfer, and now we will see this mass transfer across the interface in slow motion. Notice that the mass transfer drove the bubble into a series of spherical oscillations, not unlike what we were able to do previously. Here is a droplet rolling on the inside of the bubble. Watch what happens. Here's another droplet. It is rolling around on the inside of the surface, and the angular acceleration from circular motion that will keep the droplet in contact with the inside of the bubble, and it'll just continue to roll and roll and roll and roll. And we would have droplets roll for 45 seconds, sometimes 60 seconds, before a mass transfer event through the interface would propel the droplet away from the surface. Here's a droplet rolling in and out of the plane of the video. So a rhetorical question, is this droplet rolling like a ball across a carpet, or is it sliding like a hockey puck? If it rolls, it connotes some level of friction. Now we're using food coloring as a tracer to look at the flow into the sphere of water beyond the bubble. And notice that the flow field into the sphere makes vortex rings, which is not surprising considering what we learned before. Watch this droplet. It is filled with mica flakes, and you can see that it looks like this droplet is rolling. Drop, but notice it is rolling 90 degrees to its direction of circular motion. So from this we conclude that these droplets are sliding like hockey pucks, and they may have some initial rotational momentum. Here you can see the tracer particles forming what look like polar cap clouds outside of the bubble.